I guess I feel like a little bit on the television audience. We have a nice studio audience, but I guess there's a lot of people looking in on the web, so I'll try to remember to keep myself sort of in front of the camera here. So I'm going to talk today about some work I did actually at the University of Pennsylvania, where I was before I came to Michigan. It's a little older now. A lot of this we did around 5 to 8 years ago. I'm wearing my Philadelphia tie. So. But I think even though some of the things even though it's some of the references and some of the work we're going to look at here is a few years back, I think a lot of the issues that I'm going to discuss are very relevant for current work. I think some of the points I want to bring up about causal inference and population sampling have started to permeate into the epidemiological and injury research area more intensely in recent times, but I think it's still a good place maybe to kind of kick off some further conversation about these issues. So which I hope today's talk will do. So I'm going to focus on a particular example of trying to estimate the effectiveness of booster seats in children, say 2 to 8, versus the use of seat belts. It's an issue that I did a lot of work with some of my collaborators back at the University of Pennsylvania during the first decade of the century, and it also had some controversy that developed out of it sort of at the latter part of that decade, particularly with respect to economist at the University of Chicago, Steve Levitt, who's quite familiar, became quite familiar, and I guess reasonably say famous with his popular textbooks, Freakonomics and Super Freakonomics, which took on this issue and came to different conclusions than we had in terms of their effectiveness. So I think part of the reason for this has to do with concepts of confounding and selection bias, which I will focus on discussion. We're going to apply consider these issues in the estimation of the effectiveness of booster seats versus seatbelts in passenger vehicle crashes in a variety of different ways. And finally finish up with some conclusion and discussion with a little bit of focus on this issue of probability or population sampling versus convenience sampling, which also plays a role in this. So start off with a little slide here showing some pictures of infant car seats. You can see the nice little picture. I pulled this off the web of a 1930s handmade car seat for a young child. And indeed, a lot of these car seats in the sort of early part of mid part of the last century were not designed for safety, but merely for convenience, either for the parent or to get the child up so they could see out the windows and so forth. In the late 60s, there were seats developed in this fashion, and certainly by the mid-1980s, here we have a standard rear-facing car seat with a very happy little kid there. These had become standard, and laws requiring infants and toddlers, typically under the age of 2 and weights of less than 40 pounds, to be placed in these seats were becoming common. So, about the same time, this issue of seatbelt syndrome, which really had been explored and started to be understood again in mid-20th century, due to the fact that children are not really designed to fit in seatbelts designed for adults. So this might be a bit small, but essentially the key part of the issue is that a child, particularly one under the age of 8 or under 80 pounds, is typically going to be having their seatbelt right up over their abdomen, not their pelvis. And if there's a 3-point harness, it'll be going across their neck, not across their rib cage. So in the event of a crash, all this injury gets directed to the soft tissue in the abdomen or into the spinal area around the neck, not into the pelvis and rib cage, which are sturdier and can take the energy shock better. So you get somewhat systematic abdominal and neck injuries resulting from this. So so these booster seats, I guess the previous slide here is a nice example of this, are designed to get this fit correct. So we get the belt over the rib cage and the pelvis, and just to kind of look see if it's going to work. Yeah, okay. So this was a simulation from our University of Pennsylvania team. Top showing a child, or a model of a child in a booster seat, and the bottom showing the model of the same child in an identical crash in a lap belt. So you can see the energy again getting directed to the abdomen. And another feature too, often young kids, because of the irritation of having the seat belt not fitting right, will sometimes, with or without the driver knowing, slip the belt off their neck and behind their back. And so even if they're in a nominally a 3-point restraint, it becomes a lap belt, and you can see that often in more severe crash, you can get head injuries as well, resulting from literally going face down into the seat. Okay, so this previous slide showed simulation based on crash test data, right? So, but how effective are these booster seats relative to seat belts in real world conditions? Right. So we have the issue that the estimates are based on dummies, not actual children. Dummies are, they do not necessarily have exactly the same kind of, they're not flesh. They don't have biofidelity, as the slide talks about. We may not get quite accurate of injury risk, and maybe most importantly, these laboratory tests are simplistic compared with real-world crash and restraint use, right? Even if you hundreds of tests, you can't possibly encounter the whole distribution of how these things are going to be used in the real world. And indeed, a booster seat misuse, either by the child being the wrong size or by lack of correct positioning or attachment, is an issue. So, so we now had 2 studies, one of which worked with a probability sample of children in passenger vehicle crashes and who were insured through State Farm, that found reduction in injury, which is essentially IS2 injuries plus concussions, of about 60% relative to seat belts, at least for children 2 to 6. Another manuscript by Levitt found no significant difference in risk of fatalities between children in belt positioning booster seats and seat belts using the fatal accident reporting system, which is restricted, of course, to crash where someone dies. So, so each of these data sets has potentially different issues. So in the first one, it could be that the children that are restrained in seat belts have drivers with very different driving behavior than children that are restrained in booster seats. So it's really an issue of confounding, right? So there could be that there's some common cause that causes an increase in injuries and causes children to not be in booster seats, and that's artificially inflating the causal effect, which we'll define a bit more formally in a second. The causal effect of booster seats versus seat belts on injury risk. So the Levitt approach used the FAR system, as I mentioned. So in the Durban work, fatalities are pretty rare, and so the focus was on sort of moderate to severe injuries. So, however, FARS has its own issue, and I guess I would term that selection bias. So, so children who are protected by booster seats don't appear in the FARS unless someone else's dies. So to deal with this, Levitt used a clever idea of restricting the analysis to 2 or more vehicle crashes in which someone in another vehicle died. I guess it's someone else. Actually, someone else in another vehicle died. So to try and get around this problem of selection bias. So to get into the issues these papers focused on, and to maybe discuss why they came to different conclusions, I want to introduce some causal inference concepts and notations. I'm not sure how familiar people are with this. I think maybe now it's become pretty common. So, but just to put everybody on the same page here, we're going to use this potential outcomes paradigm. And so we imagine that we have an indicator y that represents whether or not a child got. We're going to restrict ourselves to situations where they're restrained. And then T will represent whether the child is in a child restraint seat or a seat belt. And so, so we want to. This is sort of where this sort of special thought comes in here. We have this notation y t in parentheses, which basically thinks about the potential outcomes under both possible scenarios. So, so this, when we have y of 1, we have their survival status had they been in a crash where they're restrained in a child restraint seat, and y of 0, which is their survival status had they been in this exact same crash, everything else identical, but just switched into a seat belt. So with this way of thinking, we basically have 4 scenarios. One in which a crash is essentially not survivable, so they would die with regardless of their restraint type. One in which the child restraint is protective, so they survive when they're in the child restraint and die if they're in the seatbelt. And the reverse, where the seatbelt's protective, so they survive in that and then die in if they were restrained in the car seat. And then there's the situation where, regardless of their restraint type, they survive the crash. So, under this type of definition, then, the relative risk associated with the child restraint use, then, is basically the fraction of crashes in which the child dies if they're in the child restraint, so basically the first and third row here, divided by the probability that they're in a crash where they would die under at least one of the seating conditions. So we basically take out the survivable crashes from the denominator. And then the denominator fraction here, the risk, if they're in the seat belt, of course, then is the chance of dying had they been restrained in the belt. So the y of 0 option. Okay, so sort of speed on that concept there. Okay, so that's all well and good, but the problem is we can't actually, even under experimental conditions, forget about ethical issues, create observe the 4 possible scenarios. So put a child in a crash into one of these 4 settings, right? You can't observe fatality outcome under both treatment arms. So, so to kind of explore this issue of selection bias, I'm going to consider just sort of a little simulated table here, where I'm going to assume for the moment that I'm not going to assume this in later analysis, but I'm going to assume just for explanation purposes that the child restraint is protective. So basically, you're going to just fall into one of these 3 categories, that we don't have the seatbelt protective option. And now I want to define, W here is basically someone else dies with a child involved, and 0 if that does not happen. And now what happens to this assumption that, if the assumption that the child restraint use is not independent of W? So it might be that drivers who use child restraints might tend to be involved in less serious crashes, either because of their own behavior or just more general community norms in the areas they're driving. So I'm going to look at 3 scenarios, one where there's essentially no relationship between CRS use and this outcome of the crash of the other driver. One that assumes that children, and just to make it a bit extreme and to show some numbers here that move, assume that children in the child restraints are 1/5 as likely to be in a crash where someone else dies, and then assume that children are 5 times likely to be in a crash where someone else dies. Okay, so so this is a little bit of thinking through this process here, but I'll walk through it a little bit. So here's my table. I'm just again kind of pulling these numbers out of the air. but they're not entirely unrealistic. So I'm assuming we have a population in which child restraints and belt use is basically a flip of a coin. We have about roughly maybe a little less than 1% of crashes that are always fatal where someone else dies. Then there's 100 crashes in which the child would survive had they been in a child restraint, but die if they're in the belt. And then maybe 10% where there's a fatality somewhere else in the crash, but the child itself is in the crash where they are survivable. And then there are these crashes where only the child dies, in these next two rows. And then finally, the crashes in which nobody dies, the large majority. So if we work through the true relative risk here, so if we could see, if we had this godlike power to drop each case into one of these categories, knowing what would happen had they been in a restraint versus a belt, we would see that there were 2,020 cases where the child would die if they were in a child restraint, and that would be out of the 2,420 cases where they would die in either the belt or the child restraint. So, whereas for the belt, because I've assumed that the child restraint is always protective, basically all the ones, basically the risk here is 1 amongst the crashes where the child could die. So the ratio of these risks is 0.83. So now if I go to the FARS only cohorts, I'm just going to do analysis looking at the FARS data. So that basically means I only can see data from these 3 cells here because someone died in the crash, besides the child, and then this cell here because the child did die in the crash. So it looks like I have 1,010 children who died, and that would be out of all the crashes in which someone died, the denominator from the CRS. And then similarly with the belt, I'd get 1,210. Out of that now 11,210 crashes where someone was belted, where the child was belted, which would give me, because I have no association here between this W and the CRS issues, about the correct, it's going to be very close to the true relative risk. There's a little bit of slippage based on the sort of marginal distributions of these, but they're quite close. Now, if I look at the data just for the full cohort data, so now I have all fatalities, all crashes in which someone survives. Now my numerator is the same, but now my denominator includes all of the crashes, and similarly over here for the children that were in belts, and things again work out to be the true relative risk. However, I get different results when I'm in the setting where children are more likely to be in a car seat in a crash in less likely to be in a car seat in a crash where others die. So in particular, my relative risk now is if I work with the same cells that I had over here, I get a relative risk of 0.72. The FARS cohort is basically going to miss these 500 kids that survive in the CRS but would die had they been restrained in a belt, and so it's going to underestimate the protectiveness of the child restraint. However, I'm not doing any adjustment here, so if I put in the full cohort, then I get a very large overestimate on the effectiveness because I'm not adjusting for the fact that there's this crash severity difference between the children in the car seats and the children that are not in the car seats. If we flip it around so the kids in the car seats are actually more likely to be in severe crashes, then everything kind of flips. The FARS cohort actually slightly underestimates the true risk. The full cohort now severely overestimates it. Okay, so Trying to give a sense here of how the selection bias issue can work when we look at FARS versus a full cohort of crashes. So to try and deal with this, we came with the idea of combining data from a probability sample of non-fatal crashes, in particular the NAS-CDS. Those of you who work in this area are, I'm sure, quite familiar with it. It's a nationally representative sample of police-reported crashes in which one vehicle was non-drivable. The FARS then is a census of crashes in which at least one person died. NAS-CDS has this additional sort of detailed crash investigation, review of medical records, and so forth. So it has more careful review of injuries, as well as a bit more detail about the nature of the crash than the FARS. But for the purposes of what we're going to do here, we can combine these data sets, in particular since we're looking at bodies as an outcome. So, indeed, that's the part of the problem with NAS-CDS. We don't really have a sufficient number of child passenger deaths for stable analysis, even though they do oversample severe crashes. On the other hand, the CDS includes a large number of survivable crashes that are relevant to obtaining this causal estimate of treatment effect, right? So, we deal with the selection bias issue by combining these data sets, but we now have remained and maybe enhanced this problem of confounding. Right, so that's the confounding. I mean, that's the selection bias issue here, right? That we're excluding these protective observations. So we had the idea to combine these non-fatal crashes with the FARS to get a probability sample of all towaway crashes. Took out the handful of non-towaways from FARS, and then they assigned the FARS a sampling rate of 1. They had a probability selection of 1. There's a census, so you can fit this into the probability selection framework. Okay, so we now looked at several different types of analyses to try and estimate this relative risk of fatality by restraint type. The first of these is logistic regression. I think you're all pretty familiar with this, but I wanted to kind of work through the concept more of a causal standpoint. And so a key assumption in logistic regression, and indeed in we're going to see in some of the other methods as well, is that once we condition on covariates, we'll talk about that in detail in a bit, but things like where the kid's sitting, the age of the child, issues about the driver, and so forth, that essentially we've randomized the treatment to which, in this case, the restraint to which the child is assigned. So formally, that means that we think about this joint distribution of the fatality under CRS use, the fatality under seatbelt use, and which restraint type to which they're assigned, that we get an independence between this joint distribution of the outcomes, potential outcomes, and the restraint in which they're actually sitting. So this assumption, if we kind of work through the details, allows us to estimate a causal effect on the restraint type. So again, the thing we're going after in terms of relative risk would be the probability of dying given that they are restrained in a child restraint seat. I mean, the probability of dying if they're restrained in a child restraint seat, given that there was a possibility of a fatality, right? So that they would have died in at least one of them, and now conditioning on these covariates, and divided by the probability of dying if they were in a seatbelt, given they would have died in at least one of them, and the covariates. So the first equality here essentially comes from this known observed confounding. So essentially, it doesn't really matter which one they're actually in. This probability will remain unchanged because it's essentially a randomized assignment. Similarly for the denominator. Then for the next equality, essentially comes from the definition of a conditional distribution, right? And the fact that the joint distribution of having a fatality under one of these arms means that the possible fatality indicator is also switched to 1. So, so we get second equality, and the final third equality, and the final equality down here on the last line comes from the fact that, again, we have this sort of randomized assignment conditional in X. So we can essentially, these two denominator probabilities will be actually equal to each other, and so they will cancel. And then over here, I've kind of done this little notational thing of switching from y of 1 equal to 1 to the observed y. And this is actually comes from another, perhaps somewhat subtle assumption, but an important one, the stable unit treatment value assumption, which essentially means that we sort of have one treatment, that being in a car seat and being in a seat belt, well, being in a car seat, what you actually observe from that child is their potential outcome for the car seat, and similarly, what you observe for the child in the seat belt is that potential outcome under the seat belt. So, so we can essentially then estimate this relative risk from observed data. Right? We observe our X's, observe what they're in, and we have observed outcome. So I guess I've also done this all in terms of relative risk, logistic regression, of course, odds ratio. Here the outcome could be viewed as rare. Alternatively, you could use a log link instead of a logistic link to get back to the relative risk. But the concept of all this, other than sort of switching from odds to relative risk in this notation, is the same. Okay, so that's sort of the causal machinery behind standard regression. There's an extended idea here so one of the issues with the sort of standard regression is we're conditioning on X, and we're requiring a specific parametric form conditioning. So we're saying that we have this, that the relative risk is going to, or the odds ratio is going to be the log odds ratio is going to be, say, a linear combination of these covariates times parameters we're estimating in the model. Ignores interactions, right? So if we include them, then we're going to have to sort of average over this joint distribution of X, which might be difficult to both stably and robustly identify. And so to deal with this, there's the idea of propensity scores was suggested by Rosenbaum and Rubin that showed that under this known observed confounders assumption, right, the same assumption we made back here, that essentially you could condition on the predicted value of being in this case in the car seat given X as a propensity score, and that we could then conditional on a particular propensity score, or perhaps a small value of propensity scores in say quintiles or deciles. We could look at the probability of, again, this is all from fully observed data, get these relative risks, and then average across them, consider interactions with respect to propensity, but if they're similar, certainly just averaging is a sensible thing to do, and get a relative risk measure. So what I've done for this discussion today is consider a little more robust alternative that assumes this balancing property of the propensity score only has to hold within the fatality strata. Right, so I'm going to be working with this combined NAS Forest data set. So depending on whether they're in a strata where someone dies in the crash or not, we estimate the propensity to be in the car seat, and then I'll skip the machinery, but with a little more work, the bottom line is we can get this equivalent relative risk measure all from fully observed data. Right, where this is Z is the predicted value of being in the car seat given covariates and fatality strata. So a third approach here, we're going to go recreate some of the at least analytic approach that Levitt suggested in his work that showed no impact of effectiveness on booster seats versus seat belts. And his idea is to restrict analysis to 2 vehicle crashes. And the key assumption here is that this unobserved confounding only needs to hold conditional on someone else dying in the vehicle. So in some sense, it's a little bit of a weaker assumption than logistic regression, but it does implicitly assume away this form of selection bias that I discussed in the little simulated table that we went through a little bit earlier. It also conditions on an X, although I think this could probably dealt with by a sort of an extension of a propensity model in the settings where these 2 vehicle crashes where someone on the other crash dies. I didn't go through that here, but I don't think that would change the result. So a final approach we're going to use is matched case control. Again, this is something many of you are probably familiar with. Right, we look at a crash in which 2 or more children were present and at least 1 child died and 1 child survived. We can then get a semi-parametric likelihood that effectively conditions on the crash circumstances. So it assumes basically randomization within a vehicle and randomization with respect to the child restraint type used, the restraint type used. So you can condition on observed factors, but probably the 2 of the most in here, age and seat row, were almost completely confounded. So, I essentially had to use unadjusted estimates. This is sort of similar to this double sampling idea, which is kind of a special case of matched case control that was introduced in the passenger vehicle injury literature quite some time back. Okay, so to get to the meat of the analysis then, we're combining data, and as I mentioned, this is a somewhat old data set. I'll come back with update things in a bit near the end. Looks at FARS and NAS data from 98 to 2003. We had about 7,800 children in the FARS data set and 1,400 children in the NAS data set. Between the 2, then about a little over 10,000 children, of which a little over 1,000 died. However, that only represents about almost 1 million overall, so the actual fatality rate was down around 1%. So for both the logistic regression and for the development of the passenger scores, we looked at pre-crash covariates, which include the age of the child, vehicle type, so truck, passenger car, van, etc. Seat row, first versus second seat, age of the driver. Some of these drivers are quite young, maybe young parents. Sometimes we have grandparents driving. There's quite a ability there. Gender of the driver and the vehicle model year. Only age of the child and vehicle type were actually independently and significantly associated with CRS use. So that's how we use those to develop our propensity scores, and got, I won't show it, we get good balance across the covariates. Propensity score quintiles, and a little hard to see for some reason, not coming quite as nice on the screen, but we did get some span. So there were some children that were in the child restraints that had very low probability of being put into those restraints, and vice versa. But there didn't seem to be any place that didn't, where there were no children that didn't have some non-trivial probability of being placed into one or the other based on these covariates. Okay, so the reveal here, we look at a sample that combines the SNAS and CDS and then the FARS only data. And we did logistic regression, both unadjusted and then adjusted for the covariates on the previous slide. We can see that unadjusted, very little impact of the child restraint. Once we adjust for those factors, it does look to be at least maybe marginally protective. In particular, if we take out, there are a few examples of some severe misuse. So these were children that were in booster seats that were not attached to they were sort of unbelted. So if we take those out, then we kind of do reach significance here. A little bit of a change. If we just restrict ourselves to the FARS only analysis, as we might expect, these seem to be less effective because of the selection bias issues that I mentioned before. So, however, logistic regression may suffer from incomplete confounding adjustment. We can't sort of magically work with the any unobserved confounders, but we can sort of reduce perhaps some of the parametric assumptions and work with a bit more robust propensity score. So the thing I just described previously. Again, doesn't really quite reach significance and does suggest that we may have some measure confounding that we haven't quite adjusted for properly in the logistic approach, although clearly moving toward protective. The restricted sample analysis idea that Levitt and Porter suggested for their estimation of effects of restraint use work with only the FARS data and find, indeed, as they pointed out in their paper, essentially no difference in the risk. And finally, the matched case control analysis, which again works just with the FARS data, but gives results that are perhaps a bit more in line with the robust propensity score analysis, although we have wider intervals here, so we really can't make any conclusive statements. So, okay, so how am I doing on time? Okay. So I'll spend one last little discussion here. I didn't, for reasons that will become obvious in a minute, I didn't sort of fit this in with the previous analysis, but I did want to talk a little bit about it. This idea of instrumental variable approaches. So kind of move away from the analyticas and consider approaches that have more of an experimental design flavor. So again, some of you may, but not all of you may be familiar with this idea of the instrumental variable. It's a variable that's independent of the joint distribution of the potential outcome, but correlated. So, I mean, you can think of the ideal situation here being a randomized trial where the instrument is basically the arm to which you are assigned. If you have essentially perfect compliance, then you have the best possible instrument, since it has to be independent from the joint distribution potential outcome because it's randomized, but it's perfectly correlated with the treatment or exposure of interest. That correlation might reduce if you have non-compliance. In our setting, we'll talk about in a second, we have both of these possibly in question, but we do the best we can with observed data. So to deal with this then, a sort of standard two-stage least squares approach regresses this endogenous treatment, right, this sort of non-randomized treatment on this randomized instrument Z, and then we regress Y on the predicted value of T given Z. So when these things are all binary, as in our example, then essentially the estimated causal effect is the difference in the outcomes under the instrumental variable arms divided by the difference in the treatment assignment under the different instrumental variable arms. So essentially, if you have say a relatively weak effect here, but also a weak instrument in the sense that there's a relatively small difference in being assigned to the treatment arm 1 for Z equal to 1 versus treatment arm 1 for Z equal to 0, and you really do push up this effect because there's sort of a small group in which this causal effect is presumably working, and so the overall population average needs to get kind of shoved up with this small denominator. So alternative approach that gives similar estimates, but I think is a bit more, fits a bit more with the sort of causal paradigm that I described before, is this idea of principal stratification. So we go back to our potential outcome setting, but now we think about the treatment assignment given the instrumental variable is a potential outcome of its own form. And we can imagine compliers, so these are people that only, in this case, whatever our instrument is, only use the car seat if their instrument is set to 1. Always takers, these are people that use car seats regardless of our instrumental value. Never takers, these are people that never use car seats. And the defiers, so whatever was done to try to improve car seat use had the opposite effect on these people. So there would be using the car seat only the case where they weren't encouraged to use it. So these strata are latent in the general case, right? All you can see is, so if somebody's using the car seat, you know they're a always taker. If they're not using it, you know they're a never taker. If they're using the car seat and the instrument's set to 1, you know they're a complier always taker. If they're not using an instrument set to 0, then you know that they're a complier or a never taker. So with the causal effect of interest, then conditions on these principal strata, in particular, predict conditions on being the complier stratum. So we look at the effect, the causal effect of this randomized instrument, randomized-like instrument, conditional on being in a setting where the instrument actually causes a change in the treatment that you take, right? So I guess I'll resolve the suspense. So the instrument we're going to look at is a change in law. So in the setting where our instrument is the introduction of a law to enforce child restraint and booster seats, then we look just amongst the drivers or parents that would only switch in the case where the law came into force, and then look at the estimated effect of the use of seat belts versus booster seats in this group. So there's a lot of non-identified things. I'm not going to get into details here, but essentially, with a couple of assumptions, particularly maybe somewhat strange, the fire class doesn't exist, and this exclusion restriction, that the effect of Z only is in compliers, so that basically you can't get any effect except through the treatment. So the always takers and never takers change in Z has no impact on them. If you do that, then you can actually get point estimates. As I mentioned, we can look at a natural experiment of sorts as booster seat laws that were being introduced to the US throughout the 2000s. So if we actually looked at this combined CDS and FARS data a couple years into the future from the previous analysis, and we have an additional problem here that the CDS is a sample of a relatively small number of primary sampling units. So there's actually only 6 counties where this change happened. So if we restrict ourselves to those 6 counties, predict complier status by age and seating position, and continue these adjustments to these other factors, we find that about 1/4 of the children were sort of in complier type settings. So that basically the rate of booster seat usage increased by about 25 percentage points as a result of the change in the law. Then we got, again, a pretty similar point estimate of around 25% reduction in risk of death, but the confidence interval is extremely wide here, so I really can't say much about this. And this actually points out one of the problems of the instrumental variable approach. First is that we actually need to continue to do some adjustments because it wasn't clear that the law was completely, that there may have been some other factors about where the law was applied and when it applied, and some changes in behavior that were parallel with that. And then, maybe more importantly, that the effect was sort of restricted to about 1/4 of the population, so it was hard to get enough power to really estimate this one. So, sorry. So, okay, so let me just wrap up here. So, again, I don't think we have conclusive evidence one or the other that child safety seats reduce risk of death in older children, but there is some evidence that it was on the order of 10 to 25%. Some of this work really focused on injury. So, I mean, it's less than the impact that we saw for injury, but that might be expected. Seatbelt syndrome typically doesn't cause death. It does cause some severe morbidity issues and so forth. It can, and certainly some of the head injuries and so forth that could be a problem. So I think this controversy, in this talk in some ways is perhaps a bit outdated, but, super freakonomics continued to claim the ineffectiveness of child restraints. And they actually did some analysis looking at injury, not death, and found similar results that there was sort of no impact of this. The TED Talk that sort of makes this claim has got about 500,000 hits. So, all right, so just to kind of wrap things up here, we're going to go in complete circle. So I have a plot here that on the left y-axis here is basically the death rate adjusted for 1 billion miles of travel for children aged 2 to 6. That are by restraint type use, so which is the right side of the y-axis. So the solid line shows child restraint booster seat use has climbed from around 30% in the turn of 2000 now to up around 80+% in 2012. Another subtle thing is that the non-restraint use actually dropped from around 5% to maybe 2 or 3%, and The remainder is, of course, it's seatbelts. See a pretty dramatic drop in the death rate by about over 50% during this time. Of course, we've been talking the whole thing, correlation is not causation, right? So how much of this is due to this change? Well, another crude final thing here is sort of a difference type thing. So I'm looking now at the death rate ratio between our children 2 to 6 and adults 21 to 64. And you can see kind of back and forth that it definitely explains some of this trend seems to be going on for all ages, but there is an additional part that is restricted just to these young children. Again, going from a reduction here, maybe more on the lines of around 30%, which maybe starts to look a little bit more like this number here. So, okay, so just one final little thought about this. This sort of probability sample, this NAS-CDS sample, kind of ran around in a lot of the discussion today, and certainly it's a probability sample, but non-probability samples are playing an increasing role in social science and epidemiological research. And clearly cost and convenience is an important part of this. But there's also been strong arguments made that we really need to move on from probability sampling in the epidemiology setting. A quote from a paper I reference here: sampling representativeness is incongruous with research goals. We want to know about causal mechanisms. We don't necessarily care. For descriptive statistics, I think everybody agrees probability samples are important. But in terms of understanding mechanisms, we don't necessarily need a physics certainly didn't have to work with random samples of air molecules to understand pressure laws and so forth. So we want to understand mechanisms. If there are interactions present, we want to know about them, not average over them. I think there's a couple of issues with this approach. One is that representative sampling versus probability sampling. So I'm not sure that everybody always understands this distinction. So in the NAS-CDS example, they heavily oversample severe crashes, but it's still a probability sample. We still have a known probability assignment. We can come back to a sample that is representative of the population through this. So it doesn't require equal probability sampling. There are advantages to design reasons to do this. And a subtle issue is that right, so implicit in this causal mechanism is having the right model, right? We want to get the model correct, relating our exposure to our outcome. So model misspecification can be an issue that can be corrected with representative samples. But if we have it right, we don't really need the representativeness. However, non-informative samples are not fixed so easily with models. And FARS, I think, gives an example of this. The Siren database, which looks at samples of passengers in severe crashes, has something of the same issues. So I think it's not necessarily, we don't use these data sets. They're critical in many ways. But probability sampling can play an important role to assist in their use and to improve and extend them. So, okay, so that's basically it. I have 5 minutes left, I guess. We can have a little bit of discussion. A few references here. I'm happy to pass along slides and references.
So has Levitt ever contacted you to discuss?
He contacted the PIs in this project, Dennis and Flora, Dennis Durbin and Flora Winston. As far as I know, they were not able to come to an understanding about sharing our internal data set, the State Farm data set. The analysis I've done are all public use data sets. I've certainly tried to write them in a fashion that they could be redone or used. He's never contacted me with questions. So
because he published this stuff in his book, and then he actually published it as a paper.
Yes.
Did he publish your stuff in between that? Did he actually reference your stuff?
Yes.
Other people did that?
Yes. And explained his reason. I mean, so it's actually there is an interesting backstory here. I think my own understanding of this was I don't want to hammer just on his work because I was sort of coming to a much deeper understanding of causal estimation and effects, and certainly about the same time his work came out, that really helped me to understand some of the problems that might have been in our work, and that these issues of confounding and sort of having this big group of survivable, or in this case, our injury case crashes where they would be uninjured in either setting. That helped clarify that for me. But at the same time, I really had some concerns about what he was doing, and also just the fact that I mean, his work sort of makes very explicit statements that there is no difference, which I think is a bit of a strong statement.
This is a very interesting study. I'm a modeler, but the model I deal with is totally different from yours. And we are doing computational models for human and we can clearly see the protective effect from the CRS and the booster. And somehow from the data that the protective effect is not as strong as what we see biomechanically. I wonder whether those difference might caused by some of the CRS misuse and that.
Right.
That the data really cannot identify those issues.
Right.
Simply say the CRS is not effective is kind of, I agree, it's a bold statement because maybe people didn't use that correctly.
Right.
And we all know that probably 60 to 70% of the people actually use the CRS not correctly.
Right.
Yeah.
Yeah. So I mean, so it also brings that's a couple of good points. I mean, so you saw a little bit of this here, right? We sort of pulled out this really severe misuse, the stuff that's obvious that we can pick out and we know would have a huge impact. You see, it does definitely improve the effectiveness of these. But it also brings up this issue of sort of what I thought about as biomechanics as public health, because understanding how these things work in a laboratory setting, understanding the biomechanics of it is obviously critical. But there's a sort of an analytic approach to sort of think about that, even using this kind of data, let alone the sort of engineering biomechanical type approach. But then there's so an example would be you want to sort of focus on a certain type of crash, right? Frontal crash. That's sort of a biomechanical type thing in this more epidemiological setting. But you're not only going to, you don't get to pick your crash. So if you sort of want to think about what the effectiveness of these things are, let's say if you're sort of focusing on this effectiveness of child restraint versus booster seats, you probably want to actually average over the distribution of crashes in the population, right? Because you can't pick that in advance, and if you're a parent, right, and you want to know if this is going to be protective, you want to know what are the odds over. I mean, I think you want to know if the odds are going to be over all the types of crashes. So I think, and CRS misuse is part of that, right? So clearly there may be an impact. So from a sort of a mixed thing, right? Because you can suggest that we might want to do some more work to improve, reduce that impact. But to the extent that it exists, you also might want to think about it. I mean, if it's sort of part of the deal of the difficulty of getting these things precisely correct, then an analysis that doesn't adjust for that is probably right.
But you're dealing with fatalities.
Yes.
Right.
In this analysis.
What's the fatality rate for children? And
right.
I mean, it's very, very small.
Right.
But when we look into the injury,
yes.
for example, that number could be easily show more effect or something that's more convincing. I would say. This is blurred.
Right. So So if we looked at injuries, we found, again, just with logistic regression analysis, about a 60% reduction. And I think there is a logic to that, although Levitt has done some work looking at injury. I don't know if he just used, I don't remember if he just used, I haven't double checked that paper. He just used bars, but focused on injury with this sort of similar method. I didn't see any effect there, which also makes me wonder about the nature of that analysis. Because I agree. I mean, injury, I think, these things are more about injury than death.
Okay. Yeah, I was curious on the analysis that you did with the restraint versus booster seats. Did you also look at belt use in that population compared to any child restraint? And what is the reliability of the information from the crash in terms of what a child was using?
Oh, I'm sorry. This is CRS versus booster seat. This is an error. This is a mix
Oh,
of child
okay.
restraints and booster seats versus belts.
Okay, okay.
I'm sorry. That's very
No.
confusing. That was a little fix that I unfixed, I guess, when I was getting this together.
So then I guess
Yeah.
the question would be
Mhm.
restraint use in these data sets and how reliable is that information for kids?
Right. So like I said, we pick up a little bit of it in there is some additional information about whether the booster seat or the child restraint was attached. There's no detail about the quality of that. And there's definitely, I'm sure, some measurement error in this because sometimes a lot of this would be done. So the NAS data was largely done through interview, as well as crash examination. The VARS is primarily from police report. So I mean, there are fatal crashes, but it's probably clear. I mean, I'm sure it's obviously I'm wiggling around. I'm sure there's probably some work that's more definite on that, but measurement error, I guess, is an issue.
Thank you. We're gonna have to end now.
Sure.
Time, but thank you so
Sure.
much.